Greetings, this is Robert van der Geijn, and this is a presentation that was prepared for a class at CMU taught by Franz Franchetti. It's a class on automatic optimization and code generation and those kind of general topics, for which the Flame project provides an example. And we'd like to subtitle this In the Footsteps of Dijkstra, because a lot of what we do makes a dream of his, goal-oriented programming for loop-based algorithms, reality. So let's start with a definition of science. And I've always thought that this was a definition of science that I found somewhere, but it turns out that if you Google this, you only find my name attached to it. So maybe this is my definition of science, which then makes it a little bit self-serving. Anyway, my definition is that science is knowledge that has been reduced to a system. And what we're going to see in this presentation is that we can make the programming of linear algebra algorithms for linear algebra operations systematic to the point where it can be automated. And a lot of the inspiration comes from Dijkstra, who has this wonderful talk in the paper he presented when he accepted the Turing Award called The Humble Programmer. And the only effective way to raise the confidence level of a program significantly is to give a convincing proof of its correctness. But one should not first make the program and then prove its correctness, because then the requirement of providing the proof would only increase the poor programmer's burden. On the contrary, the programmer should let correctness proof and program grow hand in hand. And we're going to see how much truth there is to that. So the question is, can we realize goal-oriented programming where one develops the proof of correctness hand in hand with the program, a reality for a piece of software that is as large as the dense linear algebra software stack? And we're going to see that the answer by and large is yes for a large class of operations that are supported by such a piece of software. So here's an outline. We're going to talk a little bit about the Flame project. It turns out that everything hinges on just the right notation. We're then going to talk about derivation of programs, for which we introduce something that we jokingly call a weapon of math induction for the war on error. Then we talk about how this creates a family of solutions for a given operation, which is where family values comes in. We talk about APIs so that we can represent these algorithms in code. We're going to see that the mechanism for getting to that point is so systematic that it can be made mechanical. So we talk about mechanical generation of algorithms and code. And then we talk a little bit about how even the notion of goal-oriented programming can be extended. We're not going to talk about related work, and I'll weasel out of that in a convenient way. And then finally there is a conclusion. So what about the Flame project? Well, what is Flame? People are often very confused about that, because it's a methodology, it is a library, it is many things. So let's look at this as part of two different categories. First of all, Flame is a notation for expressing dense linear algebra algorithms. It is also a weapon of math induction, what we're going to see, a very careful framework for the formal derivation of algorithms in this domain. It is a family of algorithms that result from this. It's a set of APIs so that we can take the algorithms and represent them in code. It's mechanical generation of code. But it's also a family of pieces of software. There is the BLAS-like library instantiation software, with which one can instantiate the basic linear algebra subprograms. It's a new implementation of the LAPACK library. It allows one to perform what we call algorithms by blocks on matrices that are stored by blocks. It allows one to schedule tasks with those blocks so that one can get parallelism via data dependencies. And it's a new distributed memory library called Elemental by Jack Paulson. We have done some investigations of how to design a linear algebra processor, which is an effort by Ardavan Bedram. And then we have something called design by transformation, which automates how an expert goes about optimizing the algorithms that result from the derivation process. And that's work by Brian Marker. So, and finally, we've started looking beyond dense linear algebra at tensor libraries, and that's being pursued by a graduate student named Martin Schatz. And we're going to talk remarkably little about performance, although our reputation is closely tied to attaining among the best performance on a lot of operations. And just to put everybody at ease, we understand performance. So on the left here is performance on 240 threads with 60 cores of the Xeon Phi. And we just quickly show that we can attain essentially the same performance as MKL can on that architecture. And then on the right, we do a similar comparison against the ESSL library on the chip that underlies the Blue Gene Q. And there we notice that on 60 cores, we actually do substantially better. So the point of this is that we understand performance. If you want to go read up on how we attain high performance, we have tons of papers available for you to read. Those papers you can get to, most of these papers you can get to by going to the Flame publication webpage, which is listed at the bottom here. And what we really want to do now is focus on the science that underlies a lot of what we do, which has to do with the Flame methodology. So let's start with notation. And to introduce our notation, we're going to focus on the Cholesky factorization just as a motivating example. And the Cholesky factorization starts with a symmetric positive definite matrix A, for which we wish to compute a lower triangular matrix L, known as the Cholesky factor, such that A is equal to L times L transpose. Now, if I were to go to a whiteboard and explain this algorithm to you, I might draw this square, which would represent the matrix. In the first step, you would expose a scalar up here in the top left corner, and then the algorithm would proceed by taking the square root of that scalar and overwriting alpha 1, 1 with that. Then we would take the result of that and divide it into the column below it. And then finally, we would update the rest of the matrix by something called a symmetric rank 1 update, which is just an outer product that's being subtracted off of A22. And the star up here just indicates that because the matrix is symmetric, we do not need to store the upper triangular part, nor do we need to compute with it. So that's the first step. Then we are done actually with those quadrants up here that are marked done. We have a partially updated matrix in the bottom right corner. What we need to now do is compute the Cholesky factor of that matrix in the bottom right corner, and to do so we partition again so that we can do another step of the Cholesky factorization, and we keep doing that. And then eventually we are done. Now what I want you to do is just look at this right here. Think of this as the state of the matrix as the algorithm proceeds, and you can sort of see that there is some loop going on that allows us to slide through the matrix. Okay, so let's get back to notation. Notice that we go from a state where the matrix is partially updated and parts of it are done, to exposing some submatrices within the partially updated matrix. And the way our notation expresses that is that we have different quadrants. This stands for A top left, A top right, A bottom left, A bottom right, which is repartitioned to expose submatrices. And notice that the thick line indicates that A top left has been relabeled A00, and A bottom left has its first row split off, which we have labeled with A10 transpose, and the rest with A21, etc. And notice that the lower case letter is used for vectors, So A10 transpose is a row vector, A01 is a column vector. Greek letters are used for scalars, and uppercase letters are used for matrices. So with that, we can express our Cholesky factorization as follows. You start by partitioning the matrix into 4 quadrants, where these 3 quadrants in blue are empty, so that A bottom right is all of A. You check whether you're done, which happens when that bottom right quadrant is 0 by 0. You then repartition the matrix into the pieces that are exposed so that you can update them here in the main body of the loop, and then you move this thick line forward as you slide through the matrix. And we like to think that this captures somewhat how one would explain the algorithm on a whiteboard with pictures. So this particular notation was first used in a journal publication back in 2000. We have a document in which we discuss many algorithms for many different linear algebra operations expressed with this notation that's available as a working note. And we're also now actually using this notation in a massive open online course, which is actually an introductory linear algebra course at the undergraduate level, where in week 1 we already start using this particular notation, just to demonstrate that it actually is quite intuitive even to people who have not been exposed to linear algebra before. So the general lesson to take away from this is that algorithms should be represented in a way that captures how we reason about them. And if we do that, then it's much easier to get those algorithms correct. But we can do actually we can go one step further. We can actually systematically derive the algorithm to be correct using this notation, and that's what we're going to talk about next, and we call this a weapon of math induction on the war on error. Okay, so how do you prove an algorithm correct? Well, in some undergraduate programs in computer science, one is taught the notion of a loop invariant, and the loop invariant is a state that is true at the top and the bottom of the loop regarding the contents of matrix A. Now think back of how the Cholesky factorization marched through matrix A. Every time we were done with a step, we had quadrants that were completely done and a quadrant that was partially updated, and that was the state that we were in at the top of the loop before we did an update to the matrix, and then at the bottom of the loop when we were done doing an update to the matrix. That's known as the loop invariant. Now, we created something that we call the worksheet that structures the proof of correctness of an algorithm. Here we have the worksheet that proves the Cholesky factorization correct. And what this is the algorithm itself interspersed with assertions about what must be true at the different points of the algorithm. And thereby we can reason through that the algorithm actually is correct. Now, rather than explaining to you why this particular worksheet proves the Cholesky factorization to correctly compute the Cholesky factor, what we're going to do is do what Dijkstra really wanted us to do, which is we're going to construct this proof of correctness hand in hand with the construction of the algorithm itself. And let's have a look at how we do that. So we call this the worksheet, and jokingly we call this the weapon of math induction, and how mathematical induction comes into the picture we'll see in a little while. And the important thing about the worksheet is that it structures the derivation of the algorithm hand in hand with the proof of its correctness. So here's the empty worksheet. Okay. Now, the first thing we need to do is we need to define what operation we wish to compute. So that starts with a precondition, which is the contents of the matrix A when we get started, and the postcondition, which deals with the contents of matrix A when we're finished. Well, we know that when we're finished, we want A to have been overwritten with this lower triangular matrix L. We know that L times L transpose should be the original matrix, but notice that we're overwriting A, so we can't say that L times L transpose is equal to A, and therefore we introduce this notation A hat, which represents the original contents of A. So this here merely says that before we get started, A has the original contents A hat. When we're done, A has been overwritten by L, and L times L transpose must be equal to the original matrix A. And the pre and post condition we insert into the worksheet at the top, because before we get started, A contains its original contents, and at the bottom, because when we're all finished, we want A to contain L, where L is the Cholesky factor of the original matrix A hat. Okay, so that plugs into the worksheet as we show right here. Now, the next thing we need to do is come up with the loop invariant. So one thing that's worthwhile pointing out right now in this worksheet is that we're going to fill this worksheet out in the order in which the steps show up in this left column. So what we're going to do next is we're actually going to systematically come up with a loop invariant that is going to tell us what A contains as the algorithm, as the loop proceeds. And how do we do that? Well, we start with the post condition. That expresses what must be in A when we're done. And we recognize that naturally, as part of the computation, we're going to slide through the matrix, exposing these quadrants. And the question that we now want to answer is, what should these quadrants equal when we're completely done in terms of the original matrix A? And the way we come to that, the way we figure that out is we take A, we know it's partitioned into these quadrants, and we take that expression right there and plug it in everywhere where you see A right here. So this gets plugged in for A, that gives us this right here. This gets plugged in for A hat, that gives us our expression right here. And then we do the same thing for L. It gets plugged in for L, so that comes right here. And then we have L times L transpose, and for the partitioned matrix, that comes in right here. And then the next thing we do is we multiply this out, because we're going to manipulate this particular expression into something that we can work with. So when we do that, we get this right here. A is equal to L when we're done, where the top left part of L times itself transpose must equal to the original A top left hat. Where does that come from? This times this transposed is L top left times L top left transpose, which must be equal to A top left hat. And we fill that in here. Similarly, we have to do this. Anyway, we have to multiply all of that out, and you get this expression right here. Now this tells us what must be in A when we're done, namely L, and how the different quadrants of L relate to the original contents of A. That's a constraint right here that must be true. Now, so we start with this, and we call this expression the partitioned matrix expression, or PME. Now, this represents all of the computation that in the end must be performed. As long as our loop is still executing, we won't have computed the final result, and therefore some of the computation expressed by the partitioned matrix expression will not yet have been performed. So what we can do is say we can come up with a loop invariant, the state that's only a partial computation towards the final result, by striking out some of the computation that needs to be performed to finish completely. So look at the PME. PME said that the top left is completely finished when you're done, the bottom left is completely finished when you're done, the bottom right is completely when you're finished done. Down here in the loop invariant, we say that the top left has been overwritten with the final result, the bottom left has been overwritten with the final result, but the bottom right has only been partially updated according to this right here. Now if you look at this right here carefully, you find out that in the end you can update the original part of the original A bottom right hat with L bottom left times L bottom left transpose, and then the result of that you need to compute the Cholesky factor of, and what we're choosing to do here is to update the bottom right part but not yet compute its Cholesky factor, and therefore there is still some computation to be done. So the point here is that by carefully looking at the partition matrix expression, we can come up with a condition that is reasonable to maintain in the matrix as the computation proceeds. And with the same kind of argument, you can actually come up with 3 different loop invariants that are reasonable to maintain. The exact details are a little bit beyond this talk, and they require you to look at dependence analysis of the different operations. But let's just look at the different loop invariants that we have here. The first one says that a top left has been overwritten by its final result, but the bottom left part and the bottom right part are still equal to its original contents. This one here says that the top left and the bottom left parts have been overwritten with their final results, but the bottom right part is still the original contents. And then finally we have the one that we just talked about, which is the one where the top left and the bottom left have been updated with the final result, but the bottom right part has only been partially updated. And that's the loop invariant that we're going to work with. Now here's another way of looking at these 3 different loop invariants more with pictures. Okay, so we're going to work with the third loop invariant, which is this one right here. And what you do then is you take that loop invariant and you fill it in the worksheet in 4 different places. Now, why these 4 different places? Well, let's first look at how it fits into the entire worksheet. And then notice that we focus in on the parts of that worksheet that actually matter right here. And here's the idea. If we can get into a state where the loop invariant is true right here just before the loop, notice that no computation happens as you enter the loop, therefore it must be true at the top of the loop right here. Now, if we can prove that if we are in this state at the top of the loop in this position right here, we will again be in that state at the bottom of the loop, then notice that the next time we come back to the top of the loop, it is going to be true again right here. But if we've proven that if it's true at the top, then it's true at the bottom, it will again be true at the bottom. So what that means is that every time through the loop, this state is going to be maintained. Eventually, we will get to the point where this loop guard, this condition that keeps us in the loop, is no longer true. At that point, we will drop out of the loop. But notice that the condition was true right here. We merely checked whether we needed to stay in the loop, did no computation at that point, and went down here. Therefore, the condition must be true after we get out of the loop. And if we can prove that that condition holds after the loop implies that we actually have computed the right result, notice there's no computation happening between these 2 assertions, then we know that the loop is actually correct. Now notice that we don't know whether this is loop correct because we haven't even created the algorithm. However, what we do know, what we hope to do, is to create an algorithm that has the property that these conditions are true at the indicated points. And if we can construct that algorithm, then we know it to be correct, and then we have derived that algorithm to be correct hand in hand with its proof. So where does the proof by induction come in? Well, the fact that it's true before the loop starts is the base case. The fact that if it's true at the top of the loop, then it's true at the bottom of the loop is the inductive step. By mathematical induction, then it's true every time you go through the loop. And then if you ever come out of the loop, you know it's done after the loop is done. You know it's true after the loop is done. So that's why we call this the weapon of math, induction. Okay, so notice that the postcondition actually allowed us to systematically derive the loop invariant. So what's in red here came from the definition of the operation that we wish to implement. Now what? Well, if we now look at the bottom of the loop, we want to construct an algorithm such that the loop invariant is true when we come out of the loop. We would like for the loop invariant to imply that we actually have computed the right thing. Now, A top left and L top left actually are going to correspond to the same part of the same matrix, because L is overwriting A. So if A top left becomes all of A, then A is equal to L, because A top left is equal to L top left according to the condition that we stated here. So when we're done, we know, so the condition that keeps us in the loop, we want to be that A top left is not yet all of A, so that when we come out of the loop, we know that A top left is all of A. In other words, that the condition that keeps us in the loop is no longer true, and therefore A top left is all of A. And if A top left is all of A, then L top left is all of L, and therefore we know that A has been overwritten with L. So the important thing here is that the loop invariant, together with the postcondition, gives us a condition called the loop guard, which is the condition during the condition that tells us whether or not we still need to stay in the loop. Very goal-oriented, okay, very systematic. The loop guard here is prescribed by the loop invariant and the postcondition. Okay, so we fill that into our worksheet, and now slowly but steadily we're starting to get somewhere. Now, what about the initialization? Before we start the loop, we know that we start with A containing A hat. We also know that we want to partition the matrix because we want to start sliding through matrix A and matrix L. So we know that we want to partition it into quadrants. But we also know that when we partition it into quadrants, we want to end up in a state where the loop invariant is true. Now, as long as A top left is empty, A bottom left is empty, and A bottom right is all of A, and A bottom right hat minus all of this is actually just A bottom right hat, because an empty matrix times its transpose is 0. So what does that mean? As long as we take A top left and L top left to be the empty matrices, the precondition, namely that A is equal to A hat, implies that A bottom right is equal to A bottom right hat, and that the empty matrix, of course, is equal to the empty matrix, etc., so that we are actually left in a state where the loop invariant is true. So notice that the precondition together with the loop invariant prescribes how we want to initialize our partitioning as we start sliding through matrix A and matrix L. And we fill that in the worksheet. Okay, now we're starting to run out of room, so I'm going to focus on the loop to give us a little bit of room. And what do we know next? Well, we know that we want to make progress through the matrix, so we know that we want to expose a next row and column by repartitioning, and notice how the thick line here dictates what is being partitioned. And we know that at the bottom of the loop we want to then move one row and one column across the thick line so that the top left of A starts expanding as we progress through the loop. So that tells us how to repartition the matrix in the loop, exposing parts of the matrix that may have to be updated. Okay, now things are getting interesting. We're going to focus here at the top of the loop. So notice the while here, this is the loop invariant, and now we have repartition. Now notice that repartitioning is an indexing step. There's no update happening to any of the matrices. So we can ask ourselves the question, in terms of these parts of the matrix that we are exposing, what is actually in the matrix after we have done our repartitioning? And that's just a matter of looking at the loop invariant, recognizing that A top left now has been relabeled A00, etc. A bottom left has been relabeled as the first row in the bottom left part and the rest of the matrix. So you get this little submatrix right here and so forth. So all we're doing is textual substitution of how the different quadrants are being relabeled. That gives us this expression right here. It's very systematic. And then we can do some linear algebra, working out what this expression actually means in terms of the contents, and we end up with this expression right here, which we then fill into the worksheet in red right here, and it tells us what the different parts of the matrix contain in terms of these parts of the matrix that have been exposed. And that goes into the worksheet. So the fact that the loop invariant is true right here, the fact that we need to repartition to make progress through the matrix right here in step 5a, tells us exactly what the contents in terms of the different exposed pieces of the matrix are by just doing textual substitution and a little bit of linear algebra. What we're going to do next is we're going to look at the bottom of the loop, and we're going to say we want to again be in the state where the loop invariant is true, but what is a top left is now being redefined because we're expanding a top left to include an extra column and an extra row, and therefore we can determine what the actual contents of the different regions of the matrix must be, because otherwise we're not in a state where the loop invariant is again true. So how do we do that? Well, we look at how we relabel the different parts of matrix A, the different quadrants. We look at the postcondition, and that tells us what the contents of the different parts must be. So here's the systematic way of doing that. You take the loop invariant, you do a textual substitution of what the different quadrants become, you do some linear algebra, and you end up with an expression for what must be in the different parts of the matrix at the point that's labeled step 7 and is highlighted here in red. Okay, so you plug that in and notice that we're starting to get somewhere. We have a lot of knowledge now about what must be in the matrix in order to make it so that the loop invariants are true at the different points in the loop where they must be true for the loop to be correct. So now we just look at step 6, which tells us what is in the matrix at the top of the loop, step 7, which tells us what must be in the matrix at the bottom of the loop, and we compare these two to determine how the different parts of the matrix must be updated. Now let's have a look at this. Down here it says that A00 should contain L00, where L00 times L00 transpose is equal to the original contents of A00. Up here we notice that A00 already contains L00, where L00 meets that constraint. Therefore, A00 doesn't need to be updated at all. It has the contents that we wish to have in it already. By contrast, if we look at alpha 11, we want alpha 11 to contain lambda 11. At this point here, alpha 11 actually contains alpha 11 minus L10 transpose times L10, some expression. We notice that lambda 11 squared is related to alpha 11 hat via this expression right here. And we notice that if we take this term to the other side, it is exactly what currently is contained in alpha 11. So what we conclude is that to compute lambda 11, all we need to do is take the current contents of alpha 11 and take the square root of that. And that justifies that alpha 11 should be updated by taking the square root of alpha 11. Similarly, you can look at what must be in A21, namely L21, how L21 is actually related to what is currently already in A21, and you can come up with the different updates to the matrix that then gives us the algorithm that we talked about before. Okay, so when we then plug that into the worksheet, we end up with the algorithm itself interspersed with the assertions that helped us derive the algorithm to be correct. And if we then simply erase all of the assertions that have to do with the correctness proof, we are left with the correct algorithm, which is the algorithm that we talked about before. And then you can repeat the exact same thing for the other loop invariants, which then yields 3 different algorithms. Now, we've written a lot of papers on this. The most noteworthy one is the paper that introduced the worksheet, which is highlighted here in boldface. There are several dissertations written on this. There's a book written on this, so there are lots of resources available to you if you want to look into this a little bit deeper. Anyway, now you understand a little bit about family values. It turns out to get high performance you need to come up with blocked algorithms, and those can be just as easily derived. We're not going to get into that in this particular presentation. We notice that we get multiple algorithms for the same operation, and from this family of algorithms we can then choose the best one for a given architecture, and that gives us some leverage because often we can find algorithms that map to a particular architecture better, better meaning attaining higher performance. Now, it's all very nice to derive this algorithm to be correct in this funny notation that we have, but you still need to then translate that algorithm into actual code, and there are plenty of bugs that you can introduce in that translation. So the correctness of the algorithm at this point does not imply the correctness of the implementation. Now for this, we've created a number of application programming interfaces for representing algorithms in code in such a way that the algorithm looks very much like the code, and therefore the correctness of the algorithm carries over to the correctness of the code. So we derive correct algorithms. If you translated those into traditional code, this could be error-prone. We have these APIs, which really one could think of as a domain-specific language of linear algebra that comes to the rescue. And there is a demo, if you go to this web page right here, in which I not only implement all of these algorithms in both MATLAB and in C, but I also demonstrate the performance benefits of the different algorithms. So I'm not going to do that as part of this presentation. You can go and check that video on your own. Again, there are a bunch of different papers associated with this, all of which you can get from the Flame publication webpage listed at the bottom here. Now, you may have noticed that the methodology that we use to derive algorithms is extremely systematic. And anytime as a computer scientist you run into something that's extremely systematic, you wonder whether it can be made mechanical, whether we can automate this. It's what we do as computer scientists. So we derive correct algorithms. We can translate these algorithms with APIs. Is it so systematic that it can be automated? Well, I'm now going to hand over this presentation to Professor Paolo Biantonesi, a former PhD student of mine who helped develop a lot of these methodologies that I just talked about, and he's going to show you how they have automated a lot of what we just talked about.
Hello, I take it over from here. I want to show you that what the methodology that Robert has been talking about can be fully automated. As a matter of fact, Robert mentioned several times that the whole methodology is fully prescribed. However, in his presentation there was a little bit of a hand waving, and several times he said that he would leave some details behind, hidden, because they would be tedious and the formulas would become so large that they would not fit on the screen. And first, when I was a PhD student, I started working on automation, and then one of my doctoral students, Diego Fabregat, took over, and he really went ahead and took care of all the minute details. And he also encoded a good amount of numerical linear algebra, of linear algebra rules, and put them into Mathematica. So now let me show you that this system, this is an interface that connects to Mathematica server back in Germany, And as I said, this Mathematica server knows this flame methodology that Robert presented, and it knows also quite a bit of linear algebra. Let's see what we can do. If I, since you have heard about the Cholesky factorization, let me go ahead and show how it can be automated. So there are two operands, one input and one output. L is an output, sorry about that, and it's a matrix, and it's lower triangular, and then we have a matrix A, which is an input matrix, and we know it's a symmetric, positive, definite. Okay, the operation that we want to perform is L times L transpose, and we want that to equal A. So this is everything that a system needs to know, and in fact this is everything that an expert would start with. Okay, I press OK. The equation, which is described by this precondition and postcondition, has been shipped to a Mathematica server. The first step was to automatically generate the partition matrix expression. Here it is. As you can see, there is only one for this specific operation. And from this partition matrix operation, 3 loop invariants were identified. The first one is then transformed into an algorithm, and as I loop over the loop invariants, the algorithms, the implementation changes. And I want to show you that if we click on details, all those details that Robert was talking about, so the loop invariant at the top of the loop, sorry, before the loop, and then at the top of the loop, and then at the bottom of the loop, all these predicates are shown, and it's then from the difference between these two predicates that the updates are described. Okay, so this is it for the Cholesky factorization. I want to show you that we can tackle significantly more involved equations. So I will talk about the Sylvester equation. Just to shorten, Sylvester. Okay, here we have 4 operands. We have a couple of triangular matrices, let's call them A and B. Then we have general matrix and the unknown matrix. So A is, let's say, lower triangular, B, let's also set it as lower triangular, C is just the general matrix, and X is the output matrix. And the Sylvester equation is defined like this: AX plus XB equals C. Once again, this is all the knowledge that is necessary to specify the equation, and it's all the knowledge that the symbolic system takes as input. Okay, the equation was a little bit more complicated, so it took a little bit longer. Here you go. This is the definition of the input, so the precondition and postcondition. Now, the important thing to notice is that we don't have only one partition matrix expression, but we have 3 of them. So 1, and for this one, we identify 2 loop invariants. Second partition matrix expression, 2 more loop invariants, and then third partition matrix expression corresponding to a 2x2 partitioning of the matrix C and X. And for this we have 16 loop invariants. And as we march through these loop invariants, you see that the algorithm is automatically updated. Okay, just to show what was going on under the cover, you see that these are the algorithms, loop invariants, and the PMEs that came from Mathematica's server. Let's see if I go up. I think that this is the, no. Yeah, this is still all the formulas. I wanted to show you the input the expression that was sent to the, here we go, yes. So this is what we sent to the mathematical server, what we inputted, and then all those pages, all this garbage right here is the encoding of all these algorithms. And from the exact same encoding, we can either represent algorithms like this or generate C and MATLAB code. Okay, I'm gonna stop with this and pass it over to Robert again. Thank you.
Okay, thank you, Paolo. And there are again a lot of different publications associated with this, some of which are listed here. Paolo's dissertation in particular has his dissertation deals with the mechanical derivation that he just demonstrated, and then there is another dissertation by one of his students that takes it one step further. Now, I'm going to very briefly talk about how goal-oriented programming needs to be extended beyond what we traditionally have thought of as goal-oriented programming. And part of that comes from the fact that these algorithms are being executed on a computer, and therefore arithmetic uses floating point arithmetic. And when you use floating point arithmetic, you incur round-off errors. And when you incur round-off errors, the whole notion of correctness changes. And there's a notion called numerical stability that one strives to achieve instead. And there are entire courses on what numerical stability means, and we don't really have time to get into that right now. However, I'd just like to point out that correctness in the presence of round-off is not the same as the correctness we just talked about. There's something called numerical stability, and the question then becomes, can we just as systematically derive numerical stability properties for these algorithms? And the answer is yes. And that, of course, is another talk, but is also dealt with in Paolo's dissertation, as well as a paper that we published in the SciM Journal on matrix, SciM Journal on Matrix Analysis and Applications, I think is what it is. Another interesting question is whether we can derive algorithms that have specific performance characteristics. So far we've talked about starting with the PME, from that deriving different loop invariants, and then deriving the algorithm that corresponds to the loop invariant. But it would be nice to be able to, from the start, say we're looking for an algorithm with certain performance characteristics. Let's just home in directly on the loop invariant that will give us those performance characteristics. And it turns out that you can recognize this from the loop invariant, and by doing so you can sidestep something that is known as the phase ordering problem for compiler technology. But that's another talk as well, and instead you can go and read the dissertation of my former student, Semeng Lo. Related work. Well, this presentation was created for a course that is going to be entirely about related work, so I'm going to cop out. So let's look at the conclusions here. What we notice is that it starts by picking the right domain. It turns out that dense linear algebra is a very nice domain to start with, and the reason is that one can march through matrices in multiple directions, and therefore one ends up with many different algorithms corresponding to different loop invariants. So it's a very rich area in which to play. What we have shown is that goal-oriented programming for loop-based algorithms has now been achieved in this domain. We believe we're quite unique in having achieved this. It has practical implications. So a lot of our libraries attain very high performance, in part because we can derive different algorithms and then pick the best algorithm for the given architecture. We have demonstrated that the approach is so systematic that it can be made mechanical, it can be automated, and there are still some extensions to be explored and not yet published.